So we're now going to talk about a motivating example for Java monitor object. And the reason for doing this is then all the other discussions we have where we talk about things like synchronized methods, synchronized statements, the wait notification mechanisms, blah, blah, blah. They'll all be in the context of a running case study that we can look at in terms of looking at real code and see the pros and cons of different features and how they build on each other and so on. And the way this is going to work, we're going to start off by looking at what not to do. And then once we understand what not to do, we're going to talk about what to do using Java's built-in monitor object synchronization and features for mutual exclusion and coordination. And we'll see that the issue here is we're going to have a so-called buggy queue that will have problems if a producer and consumer thread simultaneously call methods on that queue, and that will end up corrupting the internal state of the fields in a buggy queue object because there's no synchronization being used initially. So we'll see how this stuff works. So here's the buggy implementation, and I'll walk you through it at a high level. You can actually take a look at the code if you're interested. There's a buggy queue implementation just for fun. You can see how not to do this. And it's going to try to pass messages between a producer and a consumer thread using a buggy queue. So what the heck is a buggy queue? Well, buggy queue is a class that I implemented that's modeled on the API of the Java array bounded queue class. So we've seen array bounded queue. You saw that. Actually, it's not array bounded queue. Is it array bounded queue? I guess it's array bounded queue. Yes. And so this basically will allow you, the idea is you should be able to add and remove things in a thread safe way, but we don't implement the actual mechanisms for doing the synchronization, so of course it's not going to do what you want. Here's the UML class diagram showing the design of buggy queue. So buggy queue implements the simple blocking queue interface, which is basically what we're doing here, taking that from Java. And that will then have an implementation, as you can see here, that's going to implement these methods like put, take, poll, offer, is empty, is full, size, and so on, except it's going to do it with a linked list and an int that keeps track of the capacity. Here's a sequence diagram that shows how you might try to run this thing. Basically, you start out with a main thread. It's going to run the test. It spawns a consumer thread and a producer thread. So we make these threads, we start them, they start to run. And here's our poor, hapless buggy queue object of type buggy queue. And then the run methods of those producer and consumer threads will go in loops calling offer and poll methods. The poll method, as you might expect, will check to see if there's an item in the queue. If there is, it'll return it. If there's not, it'll return null. Offer tries to put something in the queue, and it won't block. So poll doesn't block. If the queue is empty, it just returns null. If you call offer and the queue is full, it will also just return saying, sorry, Charlie, couldn't add anything to the queue. Now, because the offer and poll methods are not synchronized, chaos and insanity will result when this app and unit test are run. So let's go ahead and take a look at the implementation. This is the implementation of buggy queue. You could always come and take a look at this thing and see what it does. But basically what it's going to do is it's just a simple wrapper around Java's linked list class. And here's what it looks like. So buggy queue implements simple blocking queue, which is just this interface that has put, take, poll, offer, is empty, is full, and size. Abstract methods, because that's what you get with interfaces unless you make them default. And this is basically a variant of what's available in Java's blocking queue interface. The implementation of this thing is just going to be a simple linked list. A simple linked list, as you are most likely aware, has no inherent synchronization, which means it's not designed to be used in a multi-threaded program where you have multiple threads adding things and removing things from it. Here are the implementations of offer and poll. These are non-synchronized, meaning that there's no locking involved. And you can see what they do. The offer method says if the queue is not full, add something to the queue and return true, otherwise return false. And poll says if the queue is not empty, remove the first element, otherwise return null. So those are the two implementations. Again, no synchronization, no blocking. Just check to see if it's full, if you want to do an offer and add it, otherwise return false. With poll, if it's empty, return null, otherwise remove the item and return it. This code is fraught with peril when used in a multi-threaded context, hopefully for obvious reasons. And the reason why it's full of peril is because these calls to is full and is empty and add and remove are not thread safe. So if you have producer thread calling offer and a consumer thread calling poll, and they're accessing the same object at the same time, chaos and insanity will ensue. So that's the end of the overview of the motivating example. What we will do now is show how Java built-in monitor object features can be used to fix this problem.